So number one, at every point, it's only dependent on the x part of that point. So if I am looking along x equals to a constant, then those vectors, those little vectors are all going to point exactly the same way. They're all going to look exactly the same because it only changes if I change x. With me? So what's got to be true? But every time I change x, if I let x be 7, x be 8, x be 9, what's changing?
Magnitude.
Magnitude's definitely changing. Yeah. So just a real quick. So if it's 1x at the point 2, 2, what will that be? 1, 2. But at the point, so at the point 2, 2, it's going to be 1, 2. It's going to be pointing basically like that. But at the point, let's say 0, 7. In fact, 0, anything. What's it going to be? 1, 0. So all along this, anywhere that if it's on the y-axis, it's going to point 1, 0, no matter what. So if I'm right here, it's going to point 1, 0. Actually, I can make that a little longer. So all along this axis is going to be like this. You guys see that? So whenever you're trying to investigate a vector field, a very smart thing to do is to look maybe at any point you want to, but definitely look at points on the y-axis, points on the x-axis. Those are real quick giveaways, real quick things to do, just to get a feel for what's going on here. So everywhere along the y-axis, the length is 1, and they're all pointing this way. We have one point here that we looked at, just one point, the length is not 1, and it's pointing in a different direction. So that right there answers this question. Does it have constant anything? No.
Right, so when you plug a c in for x, you get 0?
It's 1 comma x. Right? So the output of plugging anything in here is the vector 1 x. So if I plug in 0c, it's going to be 1 x. Cool. You guys see that? So this definitely, and I know a lot of the stuff we've done this semester, I could say this next thing is true. It messes a little with your mind. You got to be careful because the output doesn't care that we think x, y when we look at a point. This vector could be defined any way I want it to. It could be y(x), so I just turn the point around. We've looked at one like that before. Negative y(x), a nice rotation field, that kind of thing. Right? Yeah.
So a vector doesn't necessarily have to be interpreted as I hat, j hat. Just like you said.
It still is. I mean, this would still be I plus 2j. Right?
Yeah.
But sitting at the point 2, 2. Right there. Cool? You guys see that? So at the point 2, 2, what vector is associated with it in this vector field? The vector 1, 2, or I plus 2j.
Then why didn't you just say you can describe the vector however you want?
Because I can define this function. I can define this function to be any function of x and y, any function of x and y. But we kind of, when we see this, it doesn't automatically register what that means at certain points. We're so used to, I think part of it is we think x comma y or so. I think that kind of messes it up sometimes. It'll mess with your head because a lot of these will turn that around. So if I'm anywhere where x is 0, it's always going to be 1, 0. Yeah. And in fact, you can do that any x equals any constant at all. If x equals a constant, if I'm on any like that, it's going to be 1c.
Because the x is the one that...
Yes, and we're used to associating x with the horizontal axis. So to see x
but now it
associated
defies
with
the
the
y.
y-axis.
That's what I'm talking about. Good, 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 perfect.
So,
Yeah.
so the final vector will always be interpreted as I hat, j hat.
It's definitely a vector in its own right. It's just that it can take the original point and do whatever the hell it wants to with those components.
Okay.
Yeah.
But on any point you want, won't your horizontal always be like kind of like 1?
Say again, sir?
Like since the 1 is always there for your vector, wouldn't your horizontal component always be a 1?
Yeah, this will always be a 1. This will always be a 1, that's true. So anywhere in this whole line here, so I picked the point 2, 2. What about the point 3, 2? What would that be? 1, 3. So that's this idea right here. So it'll be at 3, 2, it'll point 1, 3. It'll point a little bit steeper.
But its horizontal will always be 1, right?
It'll always be a 1. Exactly. Cool. So the point to get here is I didn't have to plot a lot of these little vectors, and they're not difficult. You just kind of force yourself to do what this says to do. It says to put the x piece there and put a 1 there. Then you step back and say, okay, what vector is that? That's 1, 0. What vector is that? That's 1, 2. Well, they're pointing in different directions, and they have a different length. Therefore, for this first part, it's variable magnitude and variable direction. Cool. Well, number 2 shows you how you can control part of that. And we actually looked at this last time. The easiest way to make every single vector in there have a same length is divided by.
Basically, make a unit vector, what difference is that?
Exactly. So now they're going to be unit vectors. Are they all going to be pointing in the same direction?
No.
Hell no. Right? If I'm at the point 1, 2, 3, it's pointing in the direction 1, 2, 3. It's pointing in whatever direction because the function is x, y, z is the vector divided by the length, right, to make it a unit vector. But it's going to be pointing in whatever direction the point is that I plug in there. How are we doing so far? So definitely on number 2, let me get my magic sheet. Yeah, constant magnitude, because they're all unit vectors, variable direction.
The only way to get constant would be to have just constants as the.
Yeah, you actually, what's the only way to possibly get like constant direction?
If they're just.
Like if it was 1, 2.
So it's really, we've seen an example where we had constant direction, but it wasn't constant magnitude. Blood flow. They were always pointing in what I call the z. I just turned the whole thing, call that the z axis. Is that cool? So they were all pointing that way, and how did we accomplish that? We didn't have dependence on that variable. We didn't have dependence on z. You guys with me? Okay. What about number 2 is B. Number 3. Yeah, I think we either did that one or the book did that one. And the way to look at that is, look at the x-axis. Look at like the point 0, 3. Let me just imagine there's a scale there. At the point 0, 3, isn't that sucker pointing straight down? As it's rotating through, right through the x-axis, it would be straight down. Right, so what did I just say? Is it 0, 3?
Yeah.
3, 0. I'm thinking ahead. It's pointing in the direction 0, negative something, right? Maybe 0, negative 3. So it looks more like part C. At positive x, it's pointing down. If it was part B, at positive x, it should be pointing up, shouldn't it? So if I have this at a positive x value, let's say the point, like I was saying, 3, 0. What's the output here? Would be 0, negative 3. So that would be pointing in what direction? Straight down. If I had it turned the other way around, that would be pointing straight up. And this one looks to be pointing straight down there.
Yep.
So that's the one it should go with. It's definitely not the first option. Who remembers what the first option is? The x, y?
It's gonna be like that.
Yeah, whatever point it is, it's pointing in that same direction to point to that point. That's that idea of a radial field. So look back at number 2 real quick. Number 2 would be a 3-dimensional radial vector field. Holy shit. Because on number 2, the output is going to be a vector that's the same as that point. So it's sort of like the position vector, you pick it up and you put it on the point. So it's pointing in exactly the same direction in all ways through this sphere. Right? Today we're going to learn about something called flux. First thing I think about is Back to the Future, but exactly. But the idea of flux is if I have a sphere and flux is a measure of how much goes through that surface. So a radial field is going to go through the sphere straight out in all these directions. That's a maximum flux. You guys kind of with me? I just threw a word out that we're going to learn later, but that's the idea. It's how much goes through that surface. So obviously if I had a rotation field and a sphere, what do you think the flux would be there? Is it going through?
No.
No, it'd be 0. Right? There'd be no flux with a circular a rotation field. Okay. What about number 4? So it's definitely not B. Is that cool? Because that should be pointing straight out. That's positive R should be pointing away. That's definitely not B.
C won't be the opposite like that. The C will be like opposite to this drawing. It's gonna be arrows.
Yeah, C would still be pointing straight out. It's still positive.
Yeah.
I want these to be, if I'm at the point 1, 2, I want it to point back in. So it should point -1, -2. Point directly back in. So that's why it's got to be A. That negative hopefully gave it away pretty quickly. It wants to be pointing in, not out. So it's got to be the negative of what it usually would be. And of course, dividing by R makes it, the length of R makes it unit vector. You can see the unit vectors on there. Cool. Number 5, I think, might have been the freakiest one, but let's see. So I got a couple of votes for C.
B, yeah.
I got a questioning vote for B.
I got a more solid, but possibly one vote for B.
All right, all right. Think about the line y = 1. What does it look like? What is it? Horizontal line. So to be normal to that, can somebody just give me, so here's y = 1. To be normal to that, you have to point how? Either straight up or straight down. It doesn't matter, right? So what could possibly be that type of thing? So like at this right here, I want to point straight up. So I don't want any what component? No x component. Yeah, so what's the only one of those that has no x component? C. You guys with me? Sort of like a y = 1 line is all x component, isn't it? It's no y component because it doesn't go up or down. It's all x component. Are you semi with me here? So how do you describe the line y = 1? You say start at the y-intercept and go a multiple of this. And what would this be? 1, 0. Right? You're only allowed to move in the x direction. So to be normal to that, you must need something that moves only in the y direction. And that's that 0, 1. Cool. Okay. I just love this stuff. Number 6. Number 6 should be something you just eat for lunch, right? I mean, grading kicks ass because it's all just derivatives. And we're all over partials now. Partials are easy, hopefully. All right, just don't forget your chain rule. That's the biggest mistake people still make. Number 7 is like 6 in reverse. Yeah, but 7 wasn't that evil, was it? You can obviously eliminate B right off the bat. There's no e to the y's in there. So
There's no chain rule, that makes it easier.
Yeah, and then if you look at 7, the first component is e to the x cosine y, and the second component is negative. So if I differentiate with respect to x, it should stay the same. So then it's got to be e to the x cosine y. That's the one that stays the same. The y component should change because fy would make cosine y go to negative sine y. Cool. So how are we doing there? Is that okay? All right. Okay.
Like 6 weeks ago.
What's that?
Like 6 weeks ago.
What, this section?
No, flux.
Oh, flux. Oh, shit. I was a little too late. Alright. So now we're going to get back into what I got into just a little bit at the end of last class. So it's not terribly easy, obviously, to draw some of these things. So let me put some of this up here. I'm not going to ask you to draw these, so don't worry about that. But the idea is pretty remarkably straightforward. What I hope. And one thing we need to understand is this. Let me see. I'm going to pull this in. So if I have R of t, right, so that would be, let's just stick with 2 dimensions right now and make it easier on me. So here's like R of t 1, and here's R of t 2. So this could be some kind of curve coming in here. Let me just stop right there and make sure you guys are with me. Yeah.
Is this still 14.1 continued, or we're gonna?
14.2. Yeah. So remember the whole idea, for example, somebody help me out here. This actually is a good exercise to do because you need to be able to do this for this section anyway. How can you get the, for example, if I said, what's the equation of the line through these points?
Don't you need a normal vector?
Final minus summation?
Not a normal vector. You need a normal vector for a plane.
Right,
So line is a lot more straightforward.
Final minus summation?
This slope.
Yeah, the slope in this case is going to be represented by a vector. And you can actually do the same thing with good old rise over run. You could represent that with a vector, because if I have some vector x, y, the slope is y over x. But for 3 parts, you know, 3 component vector, I can't do that easily. I actually have to represent the slope only using a vector. That's all I can do. Or I can write it in 3 different equations. You guys remember that? X equals x naught plus at, y equals y naught plus bt, that kind of thing. Okay. And I know it's a straight line because I only need 1 parameter to define it. Okay. So how do I'm going to pick that to be my initial point. Why the hell not? So then how do I find my direction vector?
Q minus P. Still minus x1.
Yeah, q minus p. So I can do 6 minus 1 is 5. Negative 5 minus 7 is negative 12. 1 minus 2 is negative 1. So this is, I want you to realize, what we're doing here is, of course I had to do this in 3D, didn't I? But let me just kind of roughly make a crude thing about, as if it's in 2D. So let's say that's P and that's Q. What we just got was this, right? So that's like the difference between this R and that R. This could be R of T something or other, and this could be R of T something or other. Does this sound familiar? How can you identify curves now using T parameter? I can say R goes to this point on it, R goes to another point on it a little bit later. So it's sort of like I'm not directly giving the curve. I'm saying at this point I'm pointing at this far. At this time I'm pointing at that far. And if you keep going, you actually trace out the whole curve. That's what we were doing a while back. So now it's coming back to bite us in the ass. How do I then write the equation of this line?
Constant times that plus 1.
Yeah, it'll be, here's my initial point, so there's my position vector for that point, plus t times this. Now let me ask you, how are we doing so far? Does that look vaguely familiar? You guys remember that?
Yeah.
Okay. So it's the same thing as mx plus b. Right, it's actually mx plus b, but we get it. That's like our slope here. Okay. I was going to say one more thing, but I forgot. Oh, what if I only wanted the line segment between P and Q? What one adjustment would I have to make? What part of this actually makes it an entire line? What part of that gives me the whole line?
T goes to
T. If I let t go from negative infinity to infinity, I'm going to trace out the entire line. What if I only want from P to Q? That line segment.
Take off. Multiply by
0 to 1, I love it. Only let t go from 0. At 0, it's there. And of course, at 1, it's there, because that's how we got this, isn't it? We saw how far away that was. So at t equal to 0, it's this. And at t equal to 1, you add that in, it's there. So if you only let t go from 0 to 1, that's the line segment between P and Q. Okay, that type of thing you need to be able to do for this section. Yes?
Why isn't there a t equals 1?
I'm sorry, say again?
You said a t equals 1, it's at the other point.
Yeah, because when you make t equal to 1, t equal to 0 is that point. Cool. T equal to 1 would be 1 plus 5 is 6. And of course we're going to get that because that's where we got this from. Right? So very often in a lot of these problems, we're going to have these integrals that depend on t. A lot of them are going to be 0 to 1 because of the way that we define this. They don't have to be, but the easiest way to define a line segment is to make t go from 0 to 1, to do what we just did. Okay, cool. Let's see, where was I earlier than that? So this idea, these r's, as I let t change, at a later t, it's going to be way the hell down there, and so forth. So what's the actual, how do I get anything along the actual line? I take a difference between these two. Or to put it more in calculus terms, how do I get that direction pointing? How do I get that, this here, how do I get that from r of t directly? Derivative, I love it. Remember the tangent there is going to be r prime. That's exactly where a line is going to be equal to each other. The line is the tangent line. So if I have r of t, which points to these points on this curve, then r prime of t actually points in the direction of the curve right then. So everybody's like, great, Jeff. Okay. And r prime of t, I can think of it as velocity, how quickly I'm moving. As I change t, how quickly am I moving along that curve? Right here so far. All right, semi-decent. Okay. So in order to get like a length of a curve, want to know how long this curve is? Yeah, it's going to be arc length, but the arc length is always, it's kind of changing the definition. The circle is nice because the arc length is always defined the same way. Here, the minute I move is different. But all I have to really do, if this is r prime, if I integrate, now let me just put this down here. R prime is like a speed, right? You can think of it as going along a roller coaster possibly. R prime is my speed. So if I integrate r prime, my speed, times my time, and let's make this a little more specific. Let's say from A to B. So that'll be A to B. This would be the, let me make sure that, that's my speed, right? How we go? That would be my actual speed. The magnitude of that would be my speed. Times my time, this would be the arc length. Okay. Now let me make that a little more specific, because we're actually going to do something with that right now.
The integrated derivative, is it just the same function?
Yeah, my r of t is, if you think about it, my r of t is, it isn't exactly equal to the arc length, but it should be very related to the arc length. As it moves, my r of t, my change in my r of t is always pointing in that direction, that whatever the arc is doing. So if I'm moving along, my r of t is on, my r prime is always pointing in that direction. My difference between my r's is always pointing in that direction. It should come into play there. It makes sense. Okay. So what this actually ends up being, and actually we're going to prove it right now, if this is true, equals the arc length. And let me be a little less precise. Let me open this end up so it's just t, whatever t is. Right, so I'm not going to put t on it. Just it's going to go to t. So it'll be a to t. What would you use to take the derivative of both sides? Because what we really want, here's what we really want at the end. If I have, let me put this up here on the overhead. Back on. Let me turn off.
I think you gotta move the mouse first.
Always have the. Son, here it goes. I'm so excited. Should have been there. There it is. Okay. So this is the picture I showed you the other day. There's the surface Let me take the surface away so it's a little easier to see this curtain. What we're working towards is finding the area of this curtain. And I desperately want you to understand that the math behind this is actually a lot easier than it is at first blush. If you just think about the idea, if I can just get like a little length here, a ds in this case, the arc length here, the ds, I just have to multiply by the height, and that should be exactly what I need. So actually what I really, really want is integral f ds, and we call it along the curve. This shouldn't freak us out too much, because we've seen this, for example, integral over a region, and then we fill in the limits when we define what the hell the region is. So this is the integral over a curve, and we fill in the limits when we define what the curve is. Very often this is going to be 0 to 1, but we need to make this in terms of dt. This is what we normally know. We normally know this stuff. We normally know what r of t is, so then we want to be able to use dt. So how do I mean that? The line we just did we figure out what r of t is? I just had to give you a couple points. So if I said integrate along the line between this point and that point, you can figure out what r of t is real easy. So do I want to use this integral? This integral kind of sucks because it's ds. I want to use freaking dt, because then I can just throw in my r prime of t that I just got.
So you have to relate ds to dt.
Beautiful, there we go, now we're there. So I know that s is this integral. And it should make sense as I move along. If I add up all these little movements along this, velocity times time should equal distance. That's really all this says. Okay, maybe. So how do I, now here's the key question. Here's the one that's really easy to miss from earlier in calculus. But it's the biggest, baddest sound in theorem there is in freaking calculus. How do I differentiate both sides of this thing? How would I differentiate this?
Go back to the r prime.
With respect to t.
The differentiation. Remove the integration. So.
Yeah, so you have what's called the fundamental theorem of calculus, right? When you differentiate an integral, you're just going to get basically this thing evaluated at the endpoint there, right? So you're going to get ds equals r prime of t dt.
Evaluated from A to T?
No. Remember, the fundamental theorem of calculus is all about, it doesn't matter what this constant is. That constant doesn't matter. If you want to go back and look at the fundamental theorem of calculus, you can. But the idea is if I differentiate an integral, I should just get the original function itself back. And if it's from any constant to x, fx, dx, then I'm just going to get that fx. Okay. How are we doing so far? So ds, dt, and then I just throw the dt over there. Is that cool? So I do d by dt of both sides. So I get this, but then I'm going to throw that dt back over there. So now I have basically a change of variable, right? Instead of using ds, which I don't want because I'm going to have everything in terms of t, not s. So instead of using ds, I use this. So now this becomes okay. Yeah.
What is the meaning of the absolute value here? Or it's a magnitude?
Magnitude, exactly. Because I want a true speed for this guy. A true, true speed times time. Okay. So let's, obviously let's do a couple of concrete examples. Because this has gotten pretty freaky. And I've got a very, very recipe-ish way to do these kind of problems. Just to warn you, we're going to learn two main different types of integrals. This one is called a scalar line integral, because the function we have in here is a scalar valued function. It's not a vector field. With the other type of integral then will be an integral over a vector field. Oh shit, now that sounds freaking complicated, but it won't be. So let's do an example. I think this is somewhere in here. There we go. It's on page 975, example 1. So the steps are kind of, some of the steps should be very obvious. The first step is to figure out what R is, so then I can figure out what R prime is, right? So step 1, no, step 1 is find RT.
1, 0, 0 plus T, 1 negative.
I like it. So 1, 0, 0
Plus T.
plus T times.
1 negative 1 negative.
It'll be, well, you're going from P to Q. So 0 minus 1, negative 1, 1, 1. How are we doing so far? Is that all right? Is that the direction you want to go? It's a straight line, so it's going to be whatever direction is from here to here. So just subtract them to find that. Plus the beginning point. Okay. So I know that T's got to be between, like we said earlier, anytime you do that type of thing, it's always going to be between 0 and 1. So basically any line segment that they just give you the points, it's always going to be between 0 and 1. It's almost silly to do it a different way.
Well, it has to be 0.
No, there's other ways to do it, but
Well, unless you go back.
there's really no good reason to do it a different way. Yeah. Now be careful now. So to write this fully out, it would be 1 minus T, 1, 1. Is that cool? You guys see that?
Yeah.
1 minus T. Oh, not 1, 1. I'm being silly. T, T. Thank you. To put those together. Are we doing there? Are we okay there? Just to see what each of the components are. 1 minus T plus T plus T. So that, there you go. Right there. That's what R of T is all together. So let me just stop right there for a second. Okay. Yes, sir.
How did you get to that again?
So here?
Yeah.
So just add the components. 1 plus negative T. And then 0 plus T, and then so forth. Yeah. Okay. Cool. The reason now, in one respect, some of you guys might be like, well, why the hell would you want to do that? Because which version can you see R prime very easily? Yeah, right up here. It's got to be the slope. There it is. There's R prime. But here's the problem. Here's step 2. Rewrite the integrand in terms of R of T components. Let me do that again. So when we do this kind of integral, what points are we allowed to use? And from my domain, can anybody tell me, maybe using a color or something, what points am I allowed to use to find this integral? What points am I allowed to use? Here's my domain, the xy plane, right? So what points do we want to use? Not the entire xy plane. I only want this curtain. And what do they sit over? Yeah, the black line. There you go. So I only want to use points that are on this line. In this case, it's a line, and up here it's a curve, or whatever the hell, over that curve. So I'm going to rewrite that to be a lot more specific. X can't be whatever the hell it wants to be. It can only be 1 minus T. You guys see that? Mm-hmm. What can Y be? T. And what can Z be? T. I love it. So how does that integral look now? So let's say this right here. Let's do it a little more specific. X has to be 1 minus T. Y has to be T, and Z has to be T. I can see that from my definition of my curve. That defines the points that I want to use.
Oh, because that
just that black line in the XY plane.
That has to be interpreted T.
Good point. There's another good point about why the hell we want to be able to do this, because my integral is dt, not dx, dy, or dz. I like it. Yes, sir.
So R of T between 0 and 1 is that right there?
Exactly. Cool. Okay. So this is not a great example on here, but pretend like this is straight. This would be my straight line that we just defined by R of t. It stops here and here, and this would be my function on top of that. That function there. So this is the heights, isn't it? These are the heights. And this R prime, where'd it go? Oh, it's over here. This is really the length. So if I do length times, or the width times the height, that's going to be the area of the box. If I add them all up, same old thing. Okay, maybe. Nowhere near as hard as it sounds. The hardest part about this chapter, it takes a little while to get used to this, but this is not terribly difficult. The hardest part is keeping the two types of integrals separated. We start to confuse when to do which thing. So you'll see what I mean as soon as we talk about the second type of integral. That's why in a test I'm very specific. I say do the line integral of the scalar line integral, or the integrate this vector field, blah, blah, blah. So you'll know when to do which one. So now what's the integral look like?
T minus t squared.
I like it. So 1 minus t times t. So t minus t squared
Plus 2t.
plus 2t. What's the length? Well, now we got to figure out what's r prime is negative 1, 1, 1, right? So what's the length of r prime? Because that's what I need here, right? Yeah. Length of r prime is going to be square root of 1, 1, 1, 3. And of course, t goes from 0 to 1, almost always for those line segments. So here is this written in terms of t, using the inputs that I'm allowed to use. It only makes sense. You're only allowed to use x's that are like this. All right, well, let me put that in place of x, because that's the only thing I can use.
Where did the 2t thing
Sorry?
come
Oh,
from? Where did the 2t come
here. Oh, 2z, where z is t.
Okay.
So we're just plugging and chugging into my original integral, just replacing x, y, and z with what it is. Square root of 3 is that speed factor, right? Okay. And then my limits come from my definition of RT, and of course, like I just said, for line segments, it's almost always 0 to 1. Now this is really nice to integrate.
Yeah.
You can bring this square root of 3 out. You can put those together as 3t.
Yes, just 3.
3t squared over 2 plus, minus t cubed over 3. Is that cool?
3 halves minus 3.
And then from 0 to 1, not a big deal, right? That's the easy step. Yes, sir.
ds is magnitude.
ds is your, if you have an arc, ds is really, if you have s, it's cool, because ds just points right where you're going. ds just points in the direction of this arc everywhere. So from here, it's going to point this way. From here, it's going to point that way.
So magnitude of r prime is ds.
Magnitude of r prime times time. So if you take velocity, it's actually just speed. Speed times time should equal distance. That's all that says. So to traverse this, s is the perfect variable to use, the perfect parameter, because s is actually arc length. If I use t, this is just the correction factor then. T doesn't do that line in the right time. T, depending on how I define t, I could have made t be from 0 to 8 and just cut this down by 1/8 if I wanted to, right? Then it would really take a long time to get along this line then. It still does the same line, it just takes longer for it to do so. So because of my choice of 0 to 1, I actually found out that I got to multiply by √3 to make this thing move along that line like ds would have. Okay, maybe. And we all know that depending on our choice of parameter, we could trace out a circle twice as fast, maybe. So fast that if I'm not careful, I go over twice. We've seen that before, right? Depending on choice of parameter, you could actually do a circle twice in the same time that some other parameterization would take to go just around once. That's the idea here. Our choice of parameter requires this adjustment for its speed to get through that curve. Maybe.
The number we get is the arc length, right?
The number we get, what is it physically?
The distance, or the area?
Area of the curve.
Oh, the
And what I wanted to say earlier, I forgot to say over here, was if I just do this, what do you think that is? This here by itself. It's the length. If I integrate along the curve, all the ds, I of course get the length of that curve, don't I? So what does this sound like? Remember before when we did this and there was a 1 here? And I have my limits according to my region, my freaky ass region that my teacher gives me all this weird shit. If I get this region here, what would that integral represent? The what of this? The area of that, right? It's only when I throw an f in there, an actual f that's not a constant or something, then I get a volume, because then it's going to be... Of course, in reality, this is a volume, isn't it? It's just a volume with the length, the thickness is 1, so it actually numerically is the area. So look at the correspondence here. If I put a 1 here, that's the length of the curve. If I put any other function there, that's the area under that function over the curve. And of course you could have negative if your function dips below, like always, and the book freaks out about, well, there's positive for a minute. Who cares? If it goes below, that's negative. Same thing as before. It's just the volume, not the volume, the area of this curtain between the line and the curve. I mean, not the curve, but the piece of the surface. Let me say it like that. Because here's my whole surface. And I don't want the integral of the whole surface or anything. I just want the integral along this black line. Okay. Let's do another one.
So you want now the average value of this. We'll take
Then you'd have to divide by that. You'd have to figure out the length and divide by that. You're right. Similar to the same way, if you want to know the average value over a volume, you've got to actually figure out the volume. Put a 1 in, divide by the volume.
Oh, okay.
Same way. Yeah. Here's one that's a little bit different. It's number 29. Where'd it go? Here it is. So sometimes they're going to give you R of t already. Cosine. T is 0 to 2 pi. Okay, so I don't know if you guys remember, 3 cosine t, 3 sine t by itself makes what shape? Circle of radius. Circle of radius 3. Because you square those and then take the square root. Yeah. You guys with me? The minute I add in that t, at 0, it's in the xy plane. But the minute t is not 0, where is it going now? It's going up, so it's doing this kind of thing. So if I had this to be 0, it would just be tracing out the circle in the xy plane. But the minute I add that t in there, every time I make t a little bigger, it's actually moving up, and that's why they call that a helix. So what's the first step is done for me.
Does it just cut all the work that we did? It's just to start from step 2, basically?
Yeah, exactly. That first step is done. They gave me R of t.
Yeah.
Thank you.
Needed R prime and then we just substitute the...
What can I do right now before I do any other real derivatives or anything? I can just a straight up substitution I can do right now.
Yeah. 3 sine t minus t.
Yeah, well, y is 3 sine t, 11. Z is t. You guys see that? So I still need my R prime, and then here's dt. So what's R prime?
Negative 3 sine t. 3 cosine. 1.
Everybody cool with that? Right, just take the derivatives of each piece. Gotta love that stuff. And what do I actually have to plug there? Do I plug that? Well, I can't plug a vector there. Plug that, well, the magnitude of it, right? Yeah, so the magnitude of r prime, square root of, can anybody tell us what it's going to become? 3. So 1 is almost right, except the magnitude, the factor of 3 in there, right? You'll get 9 sine squared plus 9 cosine squared. Not 3 though, it'll be 9, because it's still inside the square root. You guys with me? So it'll be 9, because sine squared plus cosine squared is 1, plus 1 squared is 1. Hello. So the magnitude of the derivative of the r is going to be square root of 10. R prime is like a tangent. Yeah.
It's not 9 sine squared plus 9 cosine squared?
It is.
But then you gotta.
But then take a 9 out and you get sine squared plus cosine squared, which is 1. Cool. So right there just goes square root of 10. So not too evil here, right? And what is this going to be from to? 0 to 2 pi. So be careful here. They just told me what it was. That's mighty nice. So now you just have to integrate. Now it's the easy step. Should be the easy step. This is a single integral. Shit. It's awesome, man. One integral. Now those are nice. So what do I get here? So I get root 10. Careful, man. Negative. From 0 to 2 pi. So I get root 10 times cosine of 2 pi is 1. So I get negative 3 minus 4 pi squared over 2. So I get, is that cool? 2 pi squared? Plus, because minus and negative, what's cosine of 0? 1, so I get plus 3. So then I get negative 2 pi squared root 10. Yay. All right. Go ahead so far.
How do you get the minus sign? What does it mean? The minus.
Well, what do you think that negative sign means? What must be true about this, the curtain in this case? It must be most of the time below. That's all. We're cool with negative areas. I don't know if your previous teachers were cool with them or not. If they try to magic their way out of explaining it, it's freaking negative area. Just deal with it. Right. So our function along that point most of the time is below, or at least it's bigger below than it is above. Right. So overall, it comes out negative.
Just bad quarter business is all.
Exactly. Bad quarter for business. This is the integral they used in, well, the Enron integral was level. Okay, so let's see how we go. You guys want to take a break? Yeah, before we get into the next form, let's do that. So come back, quarter till. Yeah, so if you have a code, and here's like R, C, and T2. Yes, but what's even better than that difference is to take the derivative, R prime, because that's going to point in the direction. Think about this though. If you think about the differences between these, as you make these smaller and smaller and smaller, it's going to end up being R prime anyway. Yeah. And we want it to be the limit that they're right on top of each other, of course. No, it's not.
How would you do it?
Well, the problem would be it's easier to set up, in terms of deltas, which is really what you're saying. It's the delta R would be the differences, right? And that eventually is going to come to the dr thing for the interval. in because of the need to figure out what ds is, to be able to replace ds with what it is.
Yeah, but DS just.
But ds, be careful, ds is not the entire length. Ds is an infinitesimally small arc length that's pointing in the right direction. So you've got to use, you can't use gross differences then, you have to use infinitesimally tiny differences, and that's what the derivative is. So in a sense, you could redo the whole thing without the derivative. You'll end up doing the derivative though. You'll end up using it, just not directly, huh? I don't know, I never tried to do it. So you're just saying like, so you're saying something like the difference between this and this as T naught goes to T1. Or even like R of T minus R of T plus H. And isn't that the derivative in a way, right? Divided by H. Isn't that basically going to be our problem? So I mean, isn't that behind the scenes in any derivative that we do? It's going to be this difference. It's got to be. But when we make it infinitesimally small, we might as well use our because that's what it is. That's what these differences become. Cool. But you have the right idea. It's just that already is in there. It's behind the scenes. It's a part of what this guy is. Cool. But that, at least you see why. I mean, it makes sense that the difference is here. And as you move these closer together, the difference is, of course, approximately this better and better and better, but that's all that this is saying. So that's why you can just go ahead and use that. Cool. I like it.